All right, let's go ahead and start. All right, so let's go over our amino acids first. What is that central carbon called with all of the functional groups coming out? Alpha carbon. What is it called when you have a positive and negative in the same structure? Zwitterionic. What is that bond formed whenever two amino acids come together? Peptide or amide? Either one's acceptable. Let's see. What's the R group for glycine? H. Alanine? CH3? Proline? Yeah, it's the CH2, 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 back to the nitrogen ring. So right here, CH2, 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 connected back to nitrogen. And let's see, 1, 2, 3, 4. We also learned valine. And what's, yeah, CH3, CH3. So it's an isopropyl group. So it looks kind of like a V. So the two we're going to learn today, so here's valine. Isopropyl, see 1, 2, 3. 3 of them. And they end in sort of that VY shape. Oops. The new one is leucine. And this is a isobutyl. Butyl meaning how many carbons? 4. So if you count coming off here, 1, 2, 3, 4. Iso meaning it's going to end in that V shape. So you see the V right here with one extra carbon tail to make the butyl part. So isobutyl. This one is essential. What does that mean? Yeah, you have to get it in your diet. This one's nonpolar, so only dispersion forces. So this one is leucine. This one's used sometimes as a flavor enhancer. It's supposed to stimulate muscle and protein synthesis in your body. So maybe if you're bodybuilding or something, this could help. And then our last one for the exam is isoleucine. Isoleucine is a sec butyl. Butyl, again, meaning 4 carbons. But if you count here, do you see 1, 2, 3, 4 as our chain here? And which carbon is connected to the amino acid part here? You see 1, 2, 1, 2, 3, 4. Do you see the second carbon of that chain is connected? That's where sec comes in, meaning your second carbon of the butyl chain. Or if you want, it looks like an L. But that is sec butyl. This one's also essential, and you need it in your diet. Know what the structure is, yeah. Recognize them, also be able to draw them. And know, well, the only ones we've learned so far, they're nonpolar group. So everything we've learned up to this point are nonpolar amino acids. So that one's isoleucine. So we have leucine, which is an isobutyl, and isoleucine, which is a sec butyl. So isobutyl and sec butyl. The first one? Here you go. Again, I posted these like under week 3 or something, this PowerPoint, the exact one. So you can also print that off. It's up to you. I don't care how you do it. But so how I'm going to start today is we're going to learn some chapter 18, and then the second half of class we'll review 16, 17. Okay? Your exam for tomorrow is almost all multiple choice. Why, you might ask? Less grading for me over the holiday. So it is. Sometimes I have to do things for myself. So it's almost all multiple choice. Which, good or bad, if you're not very good at multiple choice, then do it kind of like a workout. You know, put your hand over the answers, work it out, and then compare your answer. And I promise you, you'll probably get 10 points higher if you do it that way. Okay? It'll be questions, a lot of them similar to what you've seen in multiple choice, but in addition to, like, we might have a predict the product. Okay? But obviously you're not going to draw anything. You're just going to have to tell me. So for this exam, I could have like a methyl director on there. And I could ask the next branch or the next group is going to add ortho, para, meta, or whatever choice I come up with. Okay? And you have to check which one it is, or all that apply. Or I could ask, you know, HNO3, H2SO4, what will that put on benzene? And so I might have NO2, obviously, as an answer, SO3H, and I might throw you off by putting NO3H or something like that on there, okay? So just like that, it's similar, except now you actually have choices. Does that make sense? Okay. Yes? Which nitrogen? Oh, the one. It depends if you're looking at it neutral or with the charge. You can actually draw it either way. It depends, like outside of the body, like as. Let me see how does it in there. So on here it's showing it neutral, meaning it hasn't reacted in the body yet. But as soon as it reacts with the body, that'll have a positive charge, and this one will have a negative charge. So it actually can be drawn either way. So either you draw your nitrogen and your alcohol here as neutral, or you draw them both charged. This one positive, that one negative. Any other questions on that? There are 3 workout questions. 1 predict the product, 1 synthesis, 1 mechanism. So 1 of each. And there's a bonus on there. So don't miss that whenever you get to it. Okay, so for chapter 18, we learned a little bit of naming. So let's practice with these. So let's name these 3 here. So what type of carbonyl is this top one? A ketone. So how will it end? Own. What's the longest continuous chain here? 5. So how do we name that? Pent and own. Remember the AN part will always stay in there at the end. So it's always an own if you want. Where is our ketone? Carbon 2. Any other branches? Methyl, and that's on carbon 4. So 4-methyl 2-pentanone. What sort of carbonyl is this last one here? Aldehyde? How does that end? Al? How many carbons do we have? 4, so that is butanol. Remember, we don't have to put the number on aldehydes because they always are at the end. And how do we name this? Hydroxy. And where is that located? 3. So aldehyde is always carbon 1. You don't ever have to put number 1 because it's assumed number 1. So then if that's 1, then that one's 3. And then finally, this last one, how will this one end? With which one? Yeah, al. So how many? 1, 2, 3, 4. So, yeah, butanol again. And how do we name this part right here? Oxo. And where is that? 1, 2, 3. So a alcohol as a branch is hydroxy, and a ketone as a branch is oxo. All right, looking at ketones and aldehydes, do they have hydrogen bonding? Is there hydrogen coming off that oxygen? No, but it does have the electronegative atom, so their boiling points are kind of in the middle. They're not the highest because they do not have hydrogen bonding, but they do have the electronegative atom, so it's right there in the middle. If we're looking at IR, do you remember about where a carbonyl comes in? That long 1700, so you can recognize these with IR around 1700. And then a proton NMR, so hydrogen NMR. Really the only thing is if you're next to a carbonyl, you come in around 2.1. So that's just to remind you. Let me show you some common aldehydes and ketones you might know. Here we go. Butyraldehyde. This is that gives you margarine, that butter flavor and scent. Vanillin is vanilla. Acetophenone is pistachio. Trans-cinnamylaldehyde. One day I'll get it. That's cinnamon. Carvone, that's your spearmint and caraway seeds. Anyway, you can go on. But a lot of your sort of flavor enhancers have that either an aldehyde or a ketone in them. Okay, so how do we make ketones and aldehydes? There are some old reactions that we already know that we either learned way back in Organic 1 or we've recently learned in Organic 2. So let's look at this right here, this top part. What is that? Or what does it do? Oxidizes. So you have a lot of oxygen. So what does it turn an alcohol into? A carbonyl. And you see this one will only oxidize one time because it has one hidden hydrogen. So do you see here, I know this is a large structure. That doesn't matter. It's just there to distract you. But what happened from here to the product? Alcohol turned into carbonyl. And what type of carbonyl is this? Ketone. So anytime you have a secondary alcohol, meaning this alcohol is connected to this carbon, and this carbon is connected to two other carbons, so a secondary alcohol, oxidized will always turn to a ketone. Okay, so that's one way you can make a ketone or aldehyde, oxidizing it. And this one, Chapter 18, I believe, is in the new week I just opened today. So you might not have seen it if you haven't looked at it yet. So we're in week 5, right? Okay. So I believe, has anybody seen it? It's there? Okay. So this PowerPoint is in week 5, and I think I also have a list of reactions. Are those on there too? Okay, so probably, maybe, possibly. If you don't see it, let me know, and I'll post that on there. But this one's on there. Let me show you. The list of reactions should look something like this. So here's this part. So we have alcohol, a secondary alcohol, turning into a ketone. So that's one we already know. No mechanism with this one. What if I have this? What if I have a primary alcohol with PCC? What does that do to the alcohol? It's a weak oxidizing agent. So how many times will it oxidize? Once. So the alcohol will turn into a aldehyde, carbonyl, and in this case, specifically an aldehyde. So a primary alcohol, if it oxidizes one time, so basically primary alcohol with PCC turns into your aldehyde. So now we've learned how to make a ketone, and we've learned how to make an aldehyde. Let me skip this reaction for a second, number 3, and let's go to one that we would remember. So this is what? Benzene. And what does this put on benzene? Not Cl, but the ketone. Yeah, this carbonyl group will now be on benzene. So chlorine's your leaving group with AlCl3. So basically what's in the box there will be added onto benzene. So if you see here, carbonyl, carbon-carbon is a ketone. So that's just one of your chapter 17 reactions. So we can oxidize a primary alcohol into a aldehyde. We can oxidize a secondary alcohol into a ketone. And we can put a carbonyl group onto benzene to make the ketone. Okay, so now let's look at, this one's from chapter 8. So let me redraw this one. So the most important part of this reaction is the ozone. This sulfur group, the sulfide, is just used to take the ozone off. So this one was your good surgeon. And what does the surgeon do? Cleaves. And what does it cap each side with after it cleaves? Oxygen. And since it's a good surgeon, doesn't do anything with your hydrogen? No, you leave your hydrogen coming off the double bond alone. So ozone is your good surgeon. So it's going to cleave the double bond. So do you see that it looks like I literally erased that double bond in the middle. And then again, what do we say it caps it with? Oxygen. So if I add oxygen, what type of reaction is this? Yeah, it's an oxidation. So that's what ozone does. Now let's look at what we made here. This is what? Aldehyde. And this one is a ketone. So to make an aldehyde, what do I need coming off that carbonyl? Hydrogen. And then a ketone, I'll recognize I'll make a ketone because I have 2 carbon groups. Okay, so that's all it does. If you see the ozone, that's your big hint. Just cut that double bond in half and oxidize both sides with oxygen. Okay, then we also Okay, now but before we decide what functional group's on there, what's the difference between the two? Yeah, one of them's Makarnikov, one of them's anti-Makarnikov. Which one's anti? The bottom one. What's your hint that it's that one? Peroxide. So anytime you see peroxide, this is going to be anti-Makarnikov, anti-mark. So this one will be mark. So whatever functional group we're adding, where will we add it over here? Carbon, which carbon number? 2, carbon 2. So you look at, so our original functional group on here is a triple bond. So we know whatever we're going to add on here is either going to add to this side or to that side of the triple bond. Same with if this was a double bond, it would be the same way. It's not going to add over here. Is there a functional group over there? No, so there's no reaction over there. Okay, it's all right in here. So whichever side basically is your higher degree carbon or your most substituted carbon, that's your Makarnikov carbon. So my anti-mark would be carbon 1. It'll just be the opposite. Okay, now if I just had this, now this is a triple bond, so it's going to be a little bit different, but let's pretend it's not a triple bond for a second. What would you say this adds on there? OH, right, an alcohol. So this one would add an alcohol, Makarnikov, this one would do anti-Makarnikov. But a triple bond reacts 2 times. Okay, it's almost like there's 2 bonds to react there. So I'm making, so 1 time would add a single bond to oxygen. So then 2 times would add a double bond to oxygen, which is a carbonyl. So what you're adding is a carbonyl. So over here, how many carbons total here? 4 carbons, like that, right? This one's your Makarnikov position. Now, instead of an alcohol, I actually add my carbonyl because it reacts 2 times. So and what functional group is this? Ketone. And in my bottom one, where will the carbonyl go? At the end, yeah, carbon number 1. And what's that? Aldehyde. If you don't see the aldehyde, this carbon right here, how many bonds are shown coming off of it? 3, so how many hidden hydrogens? 1, so if I draw my hidden hydrogen, it's easier to see the aldehyde. Anytime you have a carbonyl at the end, that's an aldehyde. That you don't have to draw that hydrogen there to make an aldehyde. it can be assumed. So those are all of the old reactions. So let's review those really quick again to make sure we kind of remember them. And then I'm sure we'll forget them again over turkey and cranberry sauce and everything else. Or you could start, this could be a conversation starter with your family, you know? All right, let's look on, yeah. Okay, so what does this one do? Oxidizing. So it turns my alcohol into ketone or aldehyde? Ketone, because it's secondary. PCC will turn my primary alcohol into a aldehyde. Ozone, what does that do to the double bond? Cleaves it. So this side, the left side, will turn into a aldehyde, and this right side shown will turn into a ketone. Now, it could have both been, I could have had an aldehyde on both sides if I wanted. This is just the example I put on there. What does this put on a benzene? Carbonyl, but ketone. Mercury with the triple bond puts a ketone on that carbon right there. And then the BH3 with the peroxide makes a aldehyde. There are no mechanisms with these, so the only thing you would have to do with these would be maybe synthesis, which would be the arrow part, or predict the product. No mechanism. So I just want to learn 3 new reactions, and the reason I chose 3 is because they're almost all identical. They're pretty much the same reaction. If they were 3 completely different ones, I wouldn't have done 3. But I feel like you can handle this. I have faith in you guys. So if I have this, what functional group is that? Carboxylic acid. Okay, now I know you haven't seen the lithium before. That's why it's a new reaction. But if this was Grignard, let's say magnesium chloride coming off of there, what would that add to this group? Grignard adds a carbon group. Okay? This will do the same thing. Lithium is not as reactive. Grignard sometimes is too reactive and it doesn't work very well. So in this case, with a carboxylic acid, it works better with a lithium. So it's the same thing. Lithium is on the far left of the periodic table, okay? And carbon is sort of right center, sort of. So they're very different electronegativities. So this is basically an ionic bond. So carbon has a negative, lithium has a positive. Kind of like if I have sodium chloride. Even though it's not shown, it's implied that I have a positive negative. Okay? So this is just masking my negative charge on carbon like a Grignard would. So essentially, this is just a less reactive Grignard. So where would this want to make a bond? Yeah, the carbonyl carbon. What will happen to these electrons? Go up, right? Is there anything that I can push those back down and leave? OH, and what does OH like to leave as? Water. So I can push those electrons back down to reform the carbonyl. And then where is this going to get a hydrogen to leave? H+. I kind of did the mechanism all in one step. But let's see what happens when I do this. So nothing happened to the cyclohexane. But let's look at the carbonyl. So let's look at these arrows. Do you see how they go up and then come back down? So in the end, how is my oxygen bonded? A double bond. And then OH, is that on there? No, that left is water, so I could put plus water just so you remember that it's left. And then what added on there? Benzene. So coming off here is benzene. It's also nice because Grignard a lot of times will react 2 times, right? It react again with the the ketone, but this will stop. Lithium's less reactive, so it'll stop. It only adds 1 carbon group. Yes. Lithium is in solution if you want it. Here. Okay, so this is a way you're going to have, what's my leaving group? So I have water, leaving group, LG, leaving group. And what am I adding? Well, in general, this one's benzene, but carbon group, and how many? 1. So let's put my functional group that I end up with. So I'm always adding 1 carbon group, and I always have water as my leaving group here. So what will I always end up with? A ketone. If this was benzene? Yeah, amino. This is going to be any if you want a generic one, it's just and R can be any carbon group your mind can make up. So it's a Grignard, it's like a Grignard that reacts 1 time instead of 2. So the other reaction that's very similar to this is this. All right, so that carbonyl is an acid chloride. Of all the carbonyls that we'll talk about, this is by far the most reactive. Okay, it's extremely reactive. You can make almost anything with it. Okay, so if you put just lithium alone, just like we did with the carboxylic acid, it actually will end up adding 2 carbon groups on there. And what we're trying to do, though, is trying to make a ketone or aldehyde. So we only want to add 1 carbon group. So to be able to add just 1 group at a time with this, because it's so reactive, they have to put in the copper with it. You see the copper lithium instead of just lithium? And basically that makes this reaction a little bit more mild. So it's the same reaction, except this time you just put the copper in there to help stabilize it. So what's my leaving group here? Chlorine, and if I'm adding so do you see that has 2 methyl groups? 1 methyl group is what you're adding. The other one is to stay on the copper lithium to keep it stabilized, so it won't react anymore. So so what is my carbon group I'm adding? Methyl in this case. So chlorine is my leaving group, and methyl, whatever is in this parentheses, is what you're adding. So in the end, I end up with this. Which is what? A ketone. Anytime you're adding a carbon group in this chapter, you're making a ketone. So what do you think we need to add to make an aldehyde? and a hydrogen. So this reaction is similar, except what's my leaving group here? Chlorine leaving group. What are we adding? Adding in how many carbon groups? Adding 1 carbon group. And my functional group, what do we end up with? A ketone. You'll always end up with some sort of ketone in this reaction. So basically, either I have a chlorine leaving group or a water leaving group. Both of these reactions, you're adding 1 carbon. So we've made 2 ketones. So the last reaction I want to go over today will be an aldehyde reaction, so I'm adding hydrogen. So just by looking at it, this starting material, what's my leaving group? Chlorine. Or sometimes I see it written as LiAlH. Now usually we see lithium aluminum hydride with 4 hydrogens. LiAlH, 4. Okay? This one's a strong reducing agent. Okay? But how many hydrogens do we have here? 1. So how many times do you think this will react? 1 time, because there's only 1 hydride. So this is just a source of H minus. Where will it make a bond? Yeah, this carbonyl here. The electrons will go down. Does it have something it can kick off? Chlorine. Come back down. Kick off chlorine. So what replaces chlorine? H. And what functional group did I make? Aldehyde. So that's why I decided to put all these 3 together, to group them like that, because they're so similar. Either you're adding a carbon group, which makes a ketone, or you're adding a hydride, which makes the aldehyde. But either of these reactions, either chlorine's your leaving group or water's your leaving group. So any questions with those? Okay, so let's take a break, and then we'll start reviewing for the exam. All right, let's go ahead and start the review. All right, let's see here. So for the first one, I want you to draw this in a way that reflects aromatic. So as written, what is it? Non-aromatic because of this carbon right here. So how can I make it aromatic? A negative. We could see, because how many electrons does it have right now? 4. We know we need something right there. If I left that as a positive, I would end up with what? Anti-aromatic. And then as a negative, like you were all saying, I end up with the aromatic. Label this one as aromatic, anti-aromatic, non-aromatic. Non-aromatic. Why? Nothing at the top there. That's a double. Okay, it says that, label that one and then tell me how many basic nitrogen. Aromatic? And then how many basic nitrogens? 2. And how can you tell if a nitrogen is basic? The double bonds connected. So this one has a double bond connected, so that's basic. This one has a double bond, even though it's kind of like a half double bond. Basic. So do I count those lone pairs when I'm doing the 4n plus 2 rule? No. So I just count 1, 2, 3, 4, 5, 6, which makes this aromatic. And that pretty much is chapter 16. So look over the stuff we just did and your chapter 16, is that right? Yeah, chapter 16 homework. If you could do those, fine. Any problems with those? You all seem to do pretty well on it when I was looking at your grades. So look at your chapter 16 and then the problems we just did, if you're feeling pretty confident about those. And if you missed one on there, on chapter 16, just do you know why you missed it? Okay? And that's about it. So let's look at chapter 17. Did y'all ever figure out, so we're off at noon on Wednesday, so there's no class in here. What about, I don't know when's physics? Is that 11 to 1? So is it for 1 hour? Okay, so you're like, I don't know, I'm not going to be there. And then for your, what's the other class? Trig, is there trig? No, and then AMP? Okay, so undergrad, the only class that you might have is trig. I mean, do not go to trig, but do go to AMP. Okay, so let's look at our list of reactions. Here they are. Okay, what does this put on benzene? Bromine. And so as a multiple choice, I could basically ask that, what does this reaction put on benzene? And then I could have bromine, chlorine, I don't know, whatever. And you would have to choose bromine. Does that make sense as a multiple choice? I could ask these? Okay. This one, chlorine, here, NO2. So NO2 is already on there. And this could also be the lithium aluminum hydride or sodium borohydride, NH2. This one, SO3H. What does this put on benzene? R group. Chlorine's your leaving group. What about this one here? A what? The carbonyl. It's going to put a carbonyl in there, so it puts your ketone. And then I can reduce that carbonyl. A reduction, what do I add? Hydrogen. And how many oxygen bonds do I have right now? 2. So how many hydrogens do I add? 2. So a carbonyl becomes a CH2. Kind of like up here with the same thing. You could use sodium borohydride or lithium aluminum hydride. I have how many oxygens here? 2. And then I end up with a NH2. Okay, we skip those. So if we come down to here, what does this do to benzene? It gets what? It gets rid of all the double bonds. So a benzene turns into a cyclohexane. What does KMNO4 do to a R group? Carboxylic acid. Yeah, it turns whatever carbon group into a carboxylic acid. And what does NBS and light, or you could just put Br2 and light, the same thing. So it adds bromine where? First carbon coming off benzene. So this one in particular would go off that carbon right there. So those are all of your reactions. So the reactions aren't too bad. It's applying the reactions, doing the ortho, para, meta, directing, and everything. So if we practice some of those. So let's do some like this. Okay, see if you can figure out where this next group will add. So with these, so which ones are usually your director? Your strongest directors are what? What? Well, in this case, a halogen. But your orthopara activators are always your strongest. Then would be your orthopara deactivators, because they are deactivators, but they're kind of mild deactivators. And then the least strongest director would be your meta deactivator, because those are very strong deactivators. So between a mild deactivator in chlorine or a very strong deactivator in NO2, which one's most reactive? NO2, not NO2, chlorine. So it can go ortho or para, right? So let's check all those positions we could do. Those two are both ortho, and then down here is para. Now, out of the three, which one is the least likely? The one right here, because it's why? Crowding. So what about these two here? Yeah, this would probably be a little bit more prone to go in this one, but if you wrote both reactions or both products, we find. So if we write both of them, and then let's rationalize why that one would be a little bit better. What does this put on there? SO3H. And then the other would be the para. Okay, now these, I mean, it's not going to be that much difference. It might, if I'm making up numbers, maybe 60%, 40%. Why would this one be maybe slightly more favored than that one? Crowding again. Chlorine smaller than a nitro group. Let's look at this one. So between alcohol and nitro, which one is your strongest activator? OH, your ortho-para. Ortho-para directors are, even if it's a halogen, will always be stronger sort of activators than the meta-directors. So what does BR2 and FeBr3 put on benzene? Bromine. So what positions do we need to look at for the alcohol? Directing ortho and para. So we have, again, here, here, and here. So it's pretty similar to the one we just did. If we had to choose the best position based on what we learned above, where would you choose? Let's call this 1, 2, 3. 1 is a little bit less crowded. Again, and somebody requested a couple of the sapling, and one of the sapling, if I remember correctly, deals with something like this. So let's work this one out. I believe it was this one that I pulled up. No, this one has to do with order. But this is still a good one. Okay. So let's look at this. For A, what does KMNO4 do to a methyl group? Turns it into a carboxylic acid. So I'm just going to lazily draw this. And wait, it's not going to, doesn't like that. There we go. So it turns that into a carboxylic acid. Now, what is my next group I'm going to add on there? Bromine, okay? What's my director now that's going to direct where the bromine goes? It's meta. It's the carboxylic acid. It's not the methyl, because the methyl already reacted into a carboxylic acid. So do you see that carbon's connected to oxygen? Is oxygen more electronegative? Yes, so it's going to be a meta director. So where will that be? Well, I put it, we'll say A, B, or C. B. So put your bromine there. But let's look at the one below it. Okay. What am I adding first this time? Bromine. And where will I add it? Orthopara. Why am I adding it orthopara this time? Because my director is methyl. I haven't done anything to methyl. Okay? So if I come over here. So I have my methyl. Haven't done anything with that yet. Oh, come on. And it said, if I remember, let's say you only have to draw one of them. Okay, so you either have to draw either the ortho or the para. It doesn't matter which one. So if we draw the para, I'll put my bromine right there. Okay. Now KMNO4 is my next step. What will that do to this? It'll turn this into the carboxylic acid. Right there. So the difference here is the order we do them. So this one, they're meta, but this one, they're either ortho or para, depending on which one you drew. And it's just the order because here we reacted the methyl into a carboxylic acid first, which made it a meta director. And here we didn't react that or turn that into a carboxylic acid until the end. Does that make sense on why? And then we also had a request for the last one here. Oh, it's not going to work that way. Oh, because this reaction, this was one of the reactions we skipped. But let's just look at it anyways. Chlorine is your leaving group here. And based on what's over the arrow, what do you think will replace it? OCH3. So basically where your chlorine is, you put your OCH3. Now if you put that and you're wondering why you still missed it, is because you have to put your NO2 group exactly like this. You have to show your formal charges, and you can't just put NO2, you have to actually draw it out like that. Because it says here, just show your formal charges. All right, let's look at some synthesis ones. Number 9. Ugh, that one. Okay. Let me, instead of drawing all of these, let me show you, and then we'll rationalize it, okay? Now, this first step here, we just have bromine attacking the iron, okay? Just like we've done. We're okay with that? What we're doing is the bromine mechanism on benzene. So the first thing we need to do is make a good electrophile. So we have a bromine attack the iron, which creates this bromine positive, iron negative, okay, just like we've drawn. And then it goes to the benzene reaction. So we have our good electrophile now being attacked by benzene. Okay? Now, you can see it on here, but which bromine does it like, the benzene? The neutral or the positive? The neutral. So one of your double bonds I think it actually says to make the para. So the para double bond over here will make a bond to this bromine. This whole thing leaves. Are we okay with that? Okay. So then what's the charge of benzene now that I have a bromine? Positive right there. And then what do you, I mean, you could see it, but what do we need to do? So I have a bromine there, a positive there. What's my last step? Take out the hydrogen. And hydrogen leaves its electrons there to make the double bond. And what you might have missed, it's this bond here that takes off that hydrogen. Okay, or the negative on the iodine. Usually with these, this is why I didn't want to draw it all out. It's usually something like you're missing a negative or a positive or something like that, something very, very minor. On these types that are really long like this, what is nice about it, it'll at least tell you which part you're missing. For example, it won't just say you're wrong and you have no idea which box you're wrong on. It'll at least tell you you're wrong right here. If you keep doing it over and over again and you're getting frustrated, just email me and I can pull up and see what you're doing. Okay? I could tell you, oh, you have it, you're just missing the negative on the iron. Okay? Does that make sense on how to do these? So all our benzene reactions are essentially the same, the mechanism. Benzene will attack our electrophile, which causes the giant part to leave. So that puts a positive on benzene, like we have here. And then here's our group we added. And then our final step is always take off the hydrogen, reform benzene. Now for most of our electrophile parts too, they're very similar. In this case we have bromine bonding to iron, forming our good electrophile. Now if this was chlorine and that was aluminum, what happens? The same thing, chlorine will make a bond to the aluminum. If this was a carbon group with chlorine with aluminum, what happens? Same thing, chlorine still makes a bond to the aluminum. Okay, so a lot of these, it's just your halogen attaching to either iron or aluminum, usually. The only two that are a little bit different, but still similar, would be the SO3H and the NO2 one. So let's look at those. So with NO2, we're trying to make NO2 plus. That's our goal. So if we compare this to this, what do we need to get rid of? OH as water. So my alcohol is going to grab a hydrogen, and at the same time, these electrons are going to come down to form the carbonyl. And when that happens, what do we say my leaving group was? Water. And then this turns into what? HSO4 minus. And then there's the benzene part of the reaction, which is just benzene attacks this, and then benzene reforms itself. And then with SO3H, what is my one step here I need to do? Just grab a hydrogen. So this, any of your oxygens can do it. Grab a hydrogen that leaves. And so what does this leave as? HSO4 minus. Okay, let's do a couple syntheses. And then that's pretty much it for 17 once we do the synthesis. So I'm going to draw both of these out. So work in groups and see if you can figure them out, and then we'll check them. So you need to figure out, how to put these groups on there and in the order they go on. All right, let's look at these. The first one, what is the relationship between the two? Meta. So between the two branches off of there, which one's a meta director? The top one. So which group do I put on first? NO2. How do I put NO2 on there? HNO3, H2SO4. And then how do I put methyl on there? CH3Cl with AlCl3. And the reason I knew to put it in that order and not the reverse is because the difference between the two, how far apart they are, is meta. 1, 3. So I had to put meta director on there first. Now, what about the bottom one? How far apart are they? Para, which is 1, 4. Now, between the two, which one is my para director? Bromine. So what do I put on there first? Bromine. So how do I do that? Br2, FeBr3. And then how do I put the SO3H on there? SO3 and H2SO4. Does it make sense how I know which one to put first? Because it does matter. If I reversed it, then they would be meta to each other. And it would be wrong. So a question like this on the exam, if it was multiple choice, I could give you this part right here. And then I would ask, which group do I need to put on first? Okay? And you had to tell me methyl or nitro or whatever. You know, it would have choices, but you would have to know how to do it. Okay, any questions? All right, that's about it. If you followed the review pretty well, then you're probably going to do fine on the exam.